Good afternoon, colleagues, and everyone on the call. I want to personally welcome you to today's meeting as we dive into the topic. I am very excited for the audience and to extend my thanks to the WAIMM leadership for the opportunity, an opportunity that I have not taken it for granted. Throughout this webinar, we'll aim to discuss acid rock drainage, prediction, characterization, and its monitoring in gold mines. Of course, we're looking at it from the perspective of a geologist. And I believe our discussion today will offer valuable perspective in the subject that we will be discussing. So, a brief introduction of myself. I have over 18 years experience in the industry. I started my career with Resources. I moved to Gold Mines, currently with Chirano. I've had a lot of impact on every project that I've been and achieved a lot of milestones. I would like to also emphasize that I was part of the team that did discover the Wasa underground. And at Chirano, milestones have been obvious in terms of ounce replacement, building on the portfolio where we do sit of the Sefi Gold Belt. Our presentation today is going to follow this outline. We'll look at introduction, how to characterize and predict ARD, a case study of a typical deposit that I had the opportunity to work on, mitigation measures if you are faced with an ARD in your deposit, a typical ARD cycle, and as also mentioned earlier, the questions that we look into it. Let me also mention that the formation of acid mine drainage and its contaminants and associated metals has been one of the largest environmental problems facing countries like the US. And it is important we look at where we are as an industry, some of the things that we need to do. ARD, we know, is generated as a result of exposing certain minerals within the rock types that we mine. So the question is that, what is an ARD? Basically, we are looking at sulfide minerals reacting with oxygen and water, producing or changing its state and producing hydrogen sulfate, giving a yellowish, orange, or reddish color, which the leachate leaks into the groundwater or surface water, thereby reducing the pH of the water that flows into it. Potential exists across every mining operation, in that if you look at our deposits that we mine here, majority of our mineralization styles are controlled by sulfides. And with the presence and abundance of water and oxygen, you can have an oxidative reaction that is producing sulfuric acid into the environment. The caveat therefore here is that if there's presence of neutralizing potential, and here with neutralizing potential, we are talking of the carbonate. The carbonates, if they are present in the rocks, they have the opportunity to neutralize or bring the pH down. Basically, with the sulfides, what we are looking at, all types of sulfide. We are looking at pyrite, we are looking at arsenopyrite, we are looking at pyrrhotite, and any other forms. As per our discussion, we'll focus on a particular sulfide which undergoes high oxidative reaction to produce hydrogen sulfate in terms of reducing the pH of material that flows downstream or under the groundwater system. Typically, we want to look at the situation that has happened some years back, which was a historical event that happened in the US. One of our very own WAIMM facility in Nevada experienced an acid rock drainage issue. How did it come about? During the exploration stage and prospectivity, we characterize the various rock types into economic and uneconomic. The subgrade material, which was having nearly about 0.15 to 0.2 grams per ton, had a lot of sulfide material, highly pyrite. This material was classified and dumped as wisdom, with initial perception that there was no reactivity in terms of acid rock drainage. Over a long period of time, between the startup of the mine and production, it was just a short time. During the production, within a year, over millions of tons of subgrade material has been mined and deposited. Due to environmental conditions, leachate from the waste stockpile started leaking into the groundwater and surface water, which traveled several kilometers downstream. It was recorded in 1990 that the pH of the leachate close to the source and close to the toes of the waste dams was as low as 2.3 to 3 in terms of pH, which called for an action. Now, it wasn't only the pH which was of concern. There was a release of heavy metals, for example, arsenic, copper, silver, and zinc into the effluent point. So the key message here is that it is important that we predict potential of rocks generating either acid or not during our exploration stage, during mine development stage, before we commence mining. If we fail to do that, then what is happening is that when we mine, we leave or we close the mine, there could be potential of acid rock drainage occurrence. Many of us have it in our minds that acid rock drainage occurred only in coal mines. One research has also shown that in Wicks in 1993, Johannesburg, there was serious acid rock drainage that was observed in a historical mine from their tailings down. Because the mine did not anticipate that to happen, there was a residual debt that the mine had to pay from the regulator. So as industry players, as we go about our normal duties, it's important we look at this very issue, hence the subject that we are discussing. Now let's look at the decomposition of the compound. I've already mentioned that ARD is as a result of sulfide minerals reacting with oxygen and with water, producing what we call ion 3. Ion 3 reacts rapidly, releasing an amorphous element into the environment. So if you look at how the compound reacts, you are seeing more ions precipitating in its form to form this lower pH that is always seen in surface waters and also groundwater. What do we have to do in terms of breaking this chain? A couple of things that we need to do. Let us not forget how sulfides are formed. And in this case here, I'm referring to the famous person that did enacted one of the procedures for acid rock particles, where we mentioned SUBEC 1978. It came about what we call acid-base accounting testing, where we were looking at a way of characterizing the percentage or the total sulfur content in rocks and the neutralizing potential in rocks. Two things I mentioned also here, that the neutralizing potential basically are the various carbon. We're looking at the calcite and the dolomite, whether the anchorite or any other forms of carbonate. We know that sulfides in the sedimentary environment is caused by genetic interactions of iron and sulfur. In an igneous environment, it's just coming from the magmatic fluid that cools down to form the crystal surfaces. And that is one of the elements that we are interested in making sure that they don't oxidize and get into the environment. The oxidation process is exothermic and it is very reactive, rapid, where heat exchanges, especially in stockpiles, heat exchanges forms and the leachate comes out, reducing the pH. The impact is very enormous. It pollutes surface water, it discharges into the environment, gets into the groundwater. It can travel over several kilometers. It's been found also by one Erickson and Ferguson in one of their research, 1991, where over 7,000 kilometers of leachate was able to travel that distance. So, we need to take a very key attention, put a lot of effort into this to affect our vegetation. And as minor, it also increases our rehabilitation cost when we are closing out the mine. The purpose of this is to ensure that we have clearly identified any variability within the geological unit, map it out clearly, understand whether it is a potential acid generating or whether it's a non-acid generating. And then we implement a proper plan in handling it. Within the presentation, you will hear of ARD, which I've mentioned the meaning. You'll hear of ABA, acid-base accounting, AB, which is acid potential. PAC is basically potentially acid generating, and NAD is non-acid generating. It is important to characterize during the feasibility stage of every deposit during the exploration. You need to do testing to actually establish whether there is the presence or not. The good news is if you have the neutralizing potential, then you are safe. Even that, you have to monitor it as you go along. You are assessing the various physical and chemical properties of the rocks, and you also implement a robust plan in place. So we are looking at the steps to predict an ARD. The first step is to define your geologic unit. We know that all rock types are not the same. Terminological changes are there. However, it is important for us to select our sampling such that it becomes very representative, because you are looking at a deposit where you are going to predict. It has to be very representative. There's one school of thought that states that for every deposit, based on the analysis that you have to do, you need about 8 to 12 samples that is representative of the various methodologies that is within the deposit. However, if you go to the US, the Department of Forest Service, they also mention that for every 20,000 tons of material to be mined, you need to take 1 sample. That translates into, for every 1 million tons of material to be mined, you have to take 50 samples. Now, every jurisdiction and how they come out with the sampling side. Volume is very important when you are addressing sampling for ARD prediction. When you go to British Columbia, the ARD task force has recommended that for every 40,000 tons of material to be mined, you need to take 1 sample. That also translates into, for every 1 million tons, you have to take 25 samples. So there's a bit of differences. What I recommend is that for every sampling regime that you have to do, you have to ensure that all the various or the dominant rock types that falls within your pit, it is an underground environment, that falls within your development and your stope shape, have all been sampled, representative enough for you to identify the lithologies and the units that you need. For waste dams, if it is an operational area, Because of the heterogeneity of the material there, you need to step forward and take more samples as much as you can so that it becomes very representative. So you also have to decide on the type of testing that you have to do. I am strongly inclined to the SPEC method, where it's characterized by using the ABA testing to establish the total sulfur content in it and the neutralizing potential in it. That will help you to predict the in situ variability or the in situ potential within the rocks. You can evaluate so by also doing the operational stage, conducting what we call kinetic testing. And we'll talk a little bit about the kinetic testing in the next slide to also help you to evaluate the potentials that sit within it. And it doesn't end there. You develop a model that is appropriate. You need to map out the various units, just as you are doing your normal mining sequence. You classify the various metallurgical units that are either acid forming or non-acid forming. We've already spoken about the sampling method. But let me talk a little about the static test. Like I said, the ABA testing, which was established in 1978 by SPEC, is not the only method for identifying or predicting an error. There are other methods, but this is what is industry best practice and known for characterizing it. You send the samples to the lab. If you have an internal lab, you can do it yourself. If not, you send it to the various laboratories that we have around, and the total sulfur content is established. You calculate your acid potential by multiplying it with a factor, which is 31.25, by the total sulfur content within the sample. Because you have established the XYZ locations of the sample that you send, whether it is a drill core or whether it's a grab, you have established it, you have classified the sample in terms of the lithology, be able to know the overall distribution of your sample spacing, where each and every sample sits. To also calculate the neutralizing potential, what is done normally is you add hydrochloric acid to the sample and you back calculate it and establish or measure the amount of hydrochloric acid that is consumed using the sodium hydroxide. And SPEC also recommended that the endpoint pH normally is 7. There has been a modification where the endpoint pH is 8.3, but we will not worry ourselves into that. And that is the reaction that it goes through during the calculation of this. Your net neutralizing potential is either taking a ratio or subtracting it from there. Now, I did mention about kinetic testing. The kinetic testing, once you have predicted whether there is an acid potential or not, during the operational stage, you need to also establish a way of measuring the behavior or how the rock samples are reacting to natural conditions, i.e. under air and underwater. This will help you to understand exactly how the rocks are going to react when you expose them to the environment. Like I said, the reaction is very lagging, so it can take several years for it to occur. The fact that today there is no occurrence of ARD on your mind does not mean that there's no potential. The caveat and the condition is that you need to have enough neutralizing potential within the various rock to cancel out any effect. What the carbonate basically will do is to react with the sulfides, release impurities or contaminants like calcium, aluminum, manganese, and then reduce the pH. Now, what do you do with a kinetic test? There are several forms of kinetic testing that you can implement in your mind. Some are very expensive. Like the humidity cell testing is very expensive. Like the British Columbia Research Confirmation test is very expensive. I would recommend column testing. So in one of the deposits that I worked on, we had built our own column testing where we had improvised and used it to collect samples ourselves. Now, this is what we did. We crushed the material or the various rock types. We didn't mix it. So we had different kinds. And we had crushed the material and placed it into the various containers, had a leak at the bottom where we pick the leachate every quarter and send the samples to the lab. Now, what it does is that you are exposing the samples to natural conditions. And once the samples are of the natural condition, you know the behavior of it in reacting with the sulfides. Let me go back and make mention of the fact that all of us, the deposits that we are working on within the West African Craton, I'm talking about gold, falls within these regions. There are various mineral variations, each deposit and the ingredient to gold mineralizations. For instance, if you take typical deposit on the Ashanti main belt, you're looking at pyrite contribution to enrichment of the gold. You're looking at arsenopyrite, and to some extent, you're looking at pyrrhotite, chalcopyrite, and the other groups of sulfide. All of them have the potential to react, oxidize, and reduce the pH or increase the heavy metals, the leachate that flows out to the environment. On the main Sefwi belt, and I sit on the Sefwi belt on the western margins, on the eastern margin of it. I know other deposits like Niemont also sit on the western margin of it. One of the controls to mineralization is also the presence of pyrite. If you're in the volcanics, pyrite, you cannot run away from it. Arsenopyrite, if you're in the metal segment, you cannot also run away. So elsewhere within the West African crater, the sulfide play a major role in enriching the gold that we are mining, and that is our metal of interest. So it is important we pay attention to its reactivity to the environment, and we're not looking at only what we are doing now, but in 10 years' time, in 20 years' time, after your mine closure, what will be the state of these sources of material that or runoff that is going on into the environment. We'll look at a classical case where I happen to work on two deposits where a comprehensive ARD procedure was implemented. In this very case, we sampled from diamond drill core about 917. We conducted total sulfur, organic carbon, and the various carbonate to really establish whether there is an acid potential or there is an neutralizing potential in there. So basically, depending on the lab that you send, your results may come in this form where you have your total calcium carbonate, you have your Fisher rating, and what is important is your neutralizing potential versus your maximum potential of acidity. The baseline is that if your sulfide content in terms of percentage is greater than 0.3, then you should know that it's a concern for you. The only condition is that you should have its corresponding neutralizing potential. So the threshold for the neutralizing potential is 2. If you put them on graphs and it is also greater than 2, then you know that the effect of the oxidation will be cancelled out by the carbonate. So that needs to be taken care of. So you have to ensure that the total sulfur content in there is well calculated for you. It depends if you have an in-house lab, it is easy for you to do. Now, this work that we did, the samples results came, we plotted it on a graph where we were using the percentage of sulfur versus the neutralizing potential. So in this case, this deposit actually is on the main Ashanti belt, the south central portion of it. So we're dealing with mafics, we're dealing with graphitic shear zones, greywacke, and so forth. Now, when we did plot it, so normally when you have your graph like this, if your percentage of sulfur is greater than 0.3, then you have an issue. And your utilizing potential is also less than 2, then it means that the carbonate cannot cancel out the effect. In other research, they have a way of calculating in terms of the ratio and the rest, but the net effect is the same. So with this very work that was conducted, all the rock types that fell within the lower right quadrant here had the effect. And this was a mine that had been in operation for several years. And at the wrong part, there were reactions going on, and there was no attention paid to. At the various ways down, there was a reaction also going on. And the easy thing to do is just to take the samples, analyze it, and really understand the situation. And so this work that we did, the mineralogy was such that we had arsenic content also being present, and we had salt and pyrite also being present. I'll show you another work that was conducted nearly about 40 kilometers from the first deposit, which was the deposit 1. The mineralogy of this deposit was quite different. So in terms of controls of mineralization, the total sulfide with this very deposit was only pyrite. Now, there were 2 types of pyrite there. And this is also a very interesting situation where even the shape or the textural arrangement of your sulfide has an impact on the oxidative reaction. So the pyrite that has the hydra shape is expected that the surface area is very reduced, and so it doesn't have much exposure to air and water, so the reaction is low. However, the disseminated pyrite, because it is disseminated, it has a larger surface area, so it increases the reaction, thereby increases the rate and the probability of having acid rock drainage in your rock. So with this one, deposit that samples that we took from deposit, one of them had a huge shaped pyrite, and the other was a bit disseminated, and you could see. So FWAIMM actually had pyrite which was very disseminated, and we took samples also from the feldspar, porphyry within that deposit. There was one sample which was very, so when it's at the borderline of uncertainty, and you need to investigate to really understand what the challenge or what the problem is. So with this also, we realized that the basalt from this deposit, SVW, had the potential to generate. And of course, it cannot be all the basalt in the pit, because you realize some were non-acid generating and some had even enough carbonate to cancel. As geologists, you need to look at what can you do to identify the variability in the lithologies and document it such that you will be able to have a proper model to either predict and manage the situation. So from the 2 case studies, which I was deeply involved, I realized that the phyllite actually were having potential to generate acid, and something needed to be done in there. And like I said, there was a project that was ongoing, and so it called for an immediate action. So the bat does not stop there. Once you predict and you identify there's a pack or there's a potential of acid generating in your mind, then that is when the process starts. The geologist, whether it's from exploration end or production end, needs to do detailed mapping. If it is operational stage, you have exposures. You need to do detailed mapping to really identify and delineate the various rock types that sit in there. The exploration stage, you have all the data set to be able to model it and identify where you have the issues are coming from. And you need to also calculate the volumes and tonnages that sit in the pit. Most of them are not, because exploration activities, production is always in a rush. We tend to forget about taking some of these boxes. I know some mines are implemented, but others may also not be implemented. Once you map out your area and you are able to identify the various units that contribute or have the potential to generate acid, you need to move a step further where you do the various wireframes and you have all the necessary things you have to do to put it into a computerized system. So this is what we did in one of the projects that I did work on with implementing the AI. After mapping all the rock units that was in the pit, we had to create an attribute in the block model where we had an estimated the ARD potential in there, where we were able to tell the patch zones and really include it in our planning process. So in this case, when you identify a patch zone, you need to move a step further and design your waste dam such that your waste dam for the acid generating will be different from non-acid generating. And this is where it becomes a little bit tricky. So when you are designing that waste dam, the strategies to use is different from when you are also designing a non-acid generating waste dam. And it is important we differentiate the two. Otherwise, over time, we have learned and we know that there is a possible reaction. So in managing acid potential in your mine, the geology department is of utmost importance. So just as you are mining your ore and treating it, you also need to mark out the area that has potential of generating acid, different from the raw zone. It is mined and then stockpiled in a different wisdom. During that activity also, you have to put the various boards on the various trucks that indicate that this is going to this wisdom, and communication to be very effective so that you prevent misclassification. The geologists are the baby of this very activity. If you fail to do that, what happened in the Nemo case, for instance, can also happen. And in this situation where sometimes we have our waste, our sub-grade material being treated life after mine. Your life of mine is about 20 years, and your sub-grade material has a lot of sulfides in there, and you have deposited it, and you're not monitoring. The chances are that there can be an increased rapid oxidative reaction, and the sulfide will leach into the environment, causing an ARD. So it is important we look at the implementation of this strategy. Now, if you have a mine and you do observe the potential, what are the mitigation measures that you need to put in place? The first point of call is waste capping. I did mention that where typical waste dam, you need to ensure that you have capped it even before you are dumping with about 1 meter of oxide material. That is, if it is a packed waste dam. Then after you completed dumping, you also need to cap it with the same either non-acid generating material of about 1 meter or an oxide of the same width. Before you put on your topsoil, what you are doing basically is you are reducing the inflow of air and water, and that is what is going to accelerate the reaction. One other mitigation measure that you can also do is to manage your blasting very well. Coarser grain or coarser size of rocks limits the reaction. Finer grain size liberates the sulfide, creates a lot of enough surface area, thereby allowing air water, which increases the exothermic reaction. So we recommend that during your blasting, if there is a patch zone, you will need to ensure that its blast sizes are not the same, the patterns are not the same versus the off zone. The off zones can be finer for the purpose of crashability, but for the patch zone or the waste zone, you can enlarge it to have larger boulders and so forth. I know there is other consequences, but we're looking at optimizing to reduce the surface area of the rocks that is produced. For an underground mine, what do you do when you have a potential of acid rock generation? During the mining stage at underground, you are pumping, you are reducing the water level. So you are reducing the reaction of the sulfide underground. Now, when you finish mining, first thing you need to do for the underground environment is to block or seal the portal. You're sealing the portal because you're reducing air and water runoff to go underground. That is one of the things that you can do to manage or to mitigate any reaction for an underground environment. If you also identify a packed area as an underground miner, there are other things that you can do to minimize the acid formation. If you're doing your backfilling, it is recommended that you mix it with Portland cement. What you are doing is to introduce an alkaline to the material so that when you use it as your paste backfill, you are reducing the reaction, hence neutralizing the potential. And so these are some of the mitigation measures that you can implement. I know there's a lot. Some are very costly, where you have to introduce lime and so forth. But these are very manageable, and these are a cost-effective way of managing your patch zones when there is a potential of acid generation in your deposit. So for a typical ERD cycle, I did mention that the bus doesn't stop with the geology section. It actually starts with them from exploration stage, where you go through your assessment to understand the various potentials. You send your samples to the lab and you do the analysis to predict and look at your conceptual wisdom to see whether indeed you can segregate your NAG from your pack area before mining commences. During the mining stage, you also have to ensure that you implement your kinetic testing on site to get a leachate, and the leachate is also sent to the lab to understand the dissolved metals that will also be liberated into the environment. Again, also for the mitigation measure, we spoke about making sure that you have NAG material that you are using it to encapsulate the pack areas. The geologists have a very key role to play in ensuring that in pits or underground, those material that are mined, for instance, if they are waste, they are taken to its appropriate places. If your stockpile or your low-grade stockpile, sub-grade, call it blue sky material, or think whatever it is, potential, you also need to ensure that you're putting in all the necessary steps that you need to put in to limit the reaction. The bottom line is that you want to reduce your rehabilitation and your closure cost, even after you finish mining. And one of the messages is that the reaction is very large and it can take several years to occur. We have seen a lot of mine being slapped with fines in the US because they didn't take the proper steps to manage the acid rock drainages on their deposits. I think at this stage, this is what I would like to share on the subject. Thank you very much.